take a look at section 8.3. And 8.3 is on what we call the trig form of a complex number. So we've talked about writing complex numbers as like a plus bi, like 5 plus 3i, okay, something like that. Well, writing them that way is okay, but we've seen some different things with complex numbers that get kind of cumbersome if you write them that way. And one thing would be this. If you wanted to do out something like that, it's not too bad. You just have to write 5 plus 3i. That's 5 plus 3i. And then you could FOIL it out. Okay, so we've done this kind of thing before. Now, if it's just to a power of 2, not bad. Now, if you had it to the power of 20, you'd have to write 5 plus 3i 20 times, and you'd have to distribute every factor to every factor. Okay, that's not that doable. So if we can learn how to write complex numbers in a different way, this problem is just as easy as this problem. Doesn't make a difference how big of an exponent you put. But the key is learning how to write complex numbers in what we call trig form, okay, rather than writing them in standard form. So this is standard form. Okay, what we did back, probably when we talked about quadratics and then solving when you get a square root of a negative, probably touched on it in that section. So a plus bi, the a is your real part, and the b is the imaginary part. So an example would be 3 plus 2i. That's the standard form of a complex number. Any question on that? Okay. So another way that we can represent a complex number, not quite getting into trig form, but getting us towards that, is graphically. And all you have to do to represent a complex number graphically is basically take the real part, comma, and the imaginary part. And the way we think of graphing this is kind of like an xy axis, but we don't call the axis the horizontal x, and we don't call the vertical y. What we do is we call the horizontal axis the real axis, and the vertical axis the imaginary. So if you had a point like 3 plus 2i, you identify the real part, 3. You identify the imaginary part, 2. And then you graph it. So you find 3 on the real axis. So that's right 3. You find 2 on the imaginary axis. And that's all you have to do to graph the point 3, 2. It's just like graphing a comma b. It is important that you don't switch the real and imaginary axis. It would be the same as switching the x and the y. It would be backwards. Okay, any question on how I graph that point? We're going to try a couple more. All right, so let's try graphing the point -4 minus 2i. All right, so what's my real part in that one?
-4.
-4, and this is my real axis. This is my imaginary. So which way am I going to go to get to -4 on the real axis?
Left.
Left, how many?
4.
Yep, and then the imaginary part is what?
Down 2.
Down 2. So left 4, down 2. And that's how you graph -4 minus 2i. How about -2 plus 3i? Somebody tell me how to graph that one. Yep.
Left 2, up 3.
Up 2, up 3. There you go. How about 5i? Okay.
Would just be 0 and then 5 up.
5 up. 1, 2, 3, 4, 5. So in that case, that's a pure imaginary number. There's no real part. It's just 5 up, no left and right. And then how about 6? Yep.
To the right. To the right 6?
To the right 6. Good. Right, so that's just a real number. There's no imaginary part. Now, I know you might be looking and be like, the graphing, that seems pretty easy. It is. But the point of the graphing is to kind of show you something visually. What I want to do is let's look at the point -2 plus 3i. That point has a certain distance from the origin. Okay, if you think of it as being on the circumference of a circle, so there's a certain distance away from the origin that it is, and there's a certain amount of degrees that you had to rotate to get to that point. If you can figure out those two things, that's basically how we write a complex number in trig form. Right? What is the distance it is from the origin, and then how many degrees did you rotate to get to it? So that's kind of where we're going. Anyone think they would have an idea to figure out how long that line segment is? Yeah?
Is it 180 plus -2 plus 3i?
Well, the line segment isn't going to have anything to do with a degree measure. So you won't have to use anything like 180 to find that. But it's going to be something you've used before. Yeah?
Would be Pythagorean theorem.
Yep. Do Pythagorean. Make a triangle out of that. And the two sides of the triangle, you know those from the coordinate. One of them is 2. One of them is 3. So use your Pythagorean theorem, and you've got what we call the radius, or the distance from the center. Now, to get this angle, well, think about this triangle. This is 3, this is 2. That's your reference angle. Once you find that angle, then you can do something with 180. Like let's say this angle came out to, I don't know, 60 degrees inside here. Well, to figure out that arc in red, we could just take 180 and minus the 60 from it. All right. So the idea of what we're going to be doing, we've done before, kind of thinking about, do you add 180 to your reference angle? Do you subtract it? But that's going to be the basic idea. So any questions just first on this graphing? All right. So absolute value. Well, I kind of already just showed you how to do that. What does absolute value mean visually? Yeah?
Distance from 0.
The distance from 0. Now extend that, that's a one-dimensional concept. Extend that to 2D. It'd be the distance from what? Yeah?
The origin.
The origin. So the absolute value of a complex number is just how far the number is from the origin. That's the absolute value of that number. Find the length of that line segment, which is exactly what I just explained. Use Pythagorean theorem. All right, so let's say, just as an example, you've got a point in quadrant 1. The real part is A, the imaginary part is B. So here's your point. The absolute value of that number is the distance from, we don't say 0, we say from the origin, because it's 2D. So how would you find it? A squared plus B squared equals C squared. And then you take the square root of each side, and there's your absolute value. Just like absolute value of a real number, it's always positive. Okay, so you don't want to write down a negative number because it's measuring distance. Distance can never be a negative number. Any questions on that? All right, so let's try this one. You can make a sketch if you want. I think if you just use the formula I wrote down, you don't really need it. Here's your point, and there's your triangle. So it's 3 units right, 4 units up. So what would be the absolute value of 3 plus 4i? 5. Okay, that's a 3, 4, 5 right triangle. All the rules with square roots still apply. If you get a square root that you can reduce, like square root of 20, you should be writing that as 2 square roots of 5. But in this case, we had the square root of 25, so it comes out to a nice number. Questions on that? Okay. And this 5, as I said before, is going to be one of the numbers that you need to write down when you write a complex number in trig form. Okay, the 5 is one of them. The other one is the angle. Well, I think yeah, I'm going to skip over that. We don't need to do that. So let's take a look at how we write a complex number in trig form. Now, you might also hear me say polar form because it's the same thing. Trig form, polar form. So to make this example simple, I kept the angle in quadrant 1, so the reference angle is the answer to the problem. You don't have to do a 180 minus or a 180 plus or anything like that. All right, in this example. All right. So pretend like you are given a complex number. I know we normally write it with the I after the Y, and you could put the I after it. That's normally where you put the imaginary part. But I put the I before it because it's going to work better with the formula we're going to write down. Now, the other thing is a lot of times I use A and B to represent the real and the imaginary. I'm using X and Y now because we're thinking about it visually. And I think if I write X, you'll remember better that that's horizontal. And if I use Y, you'll probably remember that's the vertical. But you could use A and B. All right, so the goal with writing a complex number in trig form is to not have an X and a Y. Okay, we want to basically come up with a formula that we could plug in for X and a formula we could plug in for Y. And the formula has to involve those two things. The distance from the origin to your point, which is basically the absolute value, and the angle that you rotated to get to your point. Right, so I kind of gave you a hint here at what two trig functions we're going to use. We're going to use sine and cosine. And let's start with cosine. Based on this diagram, what would the cosine of my angle equal? John?
Y over R. Or sorry, cosine, X over R.
X over R. So we've done this kind of thing before when we proved law of cosines. We're just getting a formula for a variable so we can replace it. I want to replace the X variable. So what is X equal to? Yep.
R cosine theta.
R cosine theta. So in a minute, that's going to go there. And now let's come up with a formula for sine. We're using sine. Yep. So sine equals opposite over hypotenuse. So y over r. And what does that mean y would equal? R sine theta. So we're going to take that and fill that in right there. And when we make those two substitutions, we're basically converting something from standard form into trig form, because now it uses trig in the expression for the complex number. That's why it's called trig form. So when you make that substitution, X is going to turn into R cosine theta. So I did that. The I is going to stay right where it is. Nothing happens to that. But the Y is going to turn into R sine theta. So I just did what the arrows are showing. Now, if you look at the right-hand side, we've got two terms. What do both terms have in common as a factor? Yep, R. So when two things have the same factor in common, what can you do? Pull it out, factor it out. So if you factor the R out, you're left with r, and then in parentheses, cosine theta plus I sine theta. That is the trig form of a complex number. So, the final answer for writing a complex number in trig form could look like this. Let's say you had a radius of 5 and an angle of 10. This is the final answer. R cosine 10 plus I sine 10. You don't do anything else with that. That is the final answer. If you try to do something more with it, let's say you say, well, I got a 5 here. Can I distribute the 5 out and then actually take the cosine of 10? Well, you could, but if you did that, you'd be changing it back to what you started with. So if you want to check your answer that way, you can do all this out and see if you get back what you started with. We'll check one of our answers, but in general, if I have to change to polar or trig form, I just stop right here. Any questions on that? Yeah.
So that's the final answer.
That would be a final answer. You would have to calculate these two values, which we've kind of already talked about using Pythagorean theorem to find your r. That's the distance from the origin. And we can use trig to find the angle of the triangle. But I'll write down those steps right now. Okay, so to use that form, you need to know the two things I just said. You have to know the radius, and you have to figure out the angle with the x-axis. So how would you actually find r and theta? Well, let's just go through it one more time, but I think people have a pretty good idea. That's r. Why do we call it r? Again, if you think of it as that point being on a circle, you're really finding the radius of a circle. Make a triangle by dropping a perpendicular to the x-axis. So this is x, and this is y. And this is r. So using that triangle, what would be the equation that I would set up to find r? Tim?
We use the log cosine. No, we use Pythagorean theorem.
Yeah. And what would you write? What would it be?
X squared plus y squared equals r squared.
Yeah, I actually have that written already right here. So to find r, you're going to use Pythagorean theorem. X squared plus y squared equals r squared. And it doesn't matter what quadrant you're in, that will always work. Now, the other thing you need is your angle. That's your angle. Now, the two things that you're going to be given are x and y. So what trig function would you use to solve for theta? Yep,
Tangent.
you'd use tangent. Because if you write down, and I'm going to write this nice and neat on the next page, but tangent of theta equals opposite over adjacent. So you'd use tangent, but that's not your answer. What would you have to do now? Yep.
The inverse tangent of y over x.
Yep. So your angle is the inverse tangent of y over x. Now, there's a little bit of a problem there. If you remember when we talk about inverse tangent has a domain of, does anybody remember the two angles that inverse tangent was always between? Like cosine was 0 to 180. We had to do that because it made inverse tangent a function. Yep.
Isn't it 0 to 90?
No, not 0 to 90. These domains are always 180 units wide, 180 degrees wide. Yep.
So 90 to 27.
So let me think, if that's not the interval we normally use, you might be able to use that interval, but it's just not the one we normally use, yeah?
Is it negative 90?
It's negative 90 to 90. So anytime you do inverse tangent, you're going to get an answer between negative 90 and 90. Well, what quadrant does that mean this formula is always going to give you an answer in? Or what quadrants? Yep.
1 and 4.
It's always going to give you an answer in quadrant 1 or 4. Well, that's not good enough because you definitely can have coordinates in quadrants 2 and 3. So how are you going to get the angle if you're in one of these two quadrants? Well, all you have to do is if you get an answer that's in quadrant 1 or 4, if you add 180 to it, it will move you to the other half of the circle, right? So when we go through it, we'll draw that out so you can see it. But when you're in quadrants 2 and 3, you can still do inverse tangent of y over x. But to take into account you're in those quadrants, you have to add 180 to your answer. So quadrants 1 and 4, inverse tangent of y over x works fine. Because this formula is built to give you an answer in those two quadrants. If you're in quadrants 2 or 3, you have to add 180 to your answer. And that'll automatically give you an answer in quadrant 2 or 3. And if you're not sure why that works, just think about if you go from negative 90 to 90, right, if that's where you are originally, and you add 180 to any number in that interval. Well, now you're going to get an answer, negative 90 plus 180, that's 90, and 90 plus 180 is 270. So that's going to shift your answer to be between 90 and 270. Well, 90 is here, 270 is here, so it's going to cover answers in quadrants 2 and 3 by adding 180 to it. Any question on that? Or you could add pi if you're doing it in radians. Now, this, using the Pythagorean theorem, covers finding the radius anywhere in the complex plane. This only covers finding theta in quadrants 1, 2, 3, and 4. Where else can theta be besides in quadrant 1, 2, 3, or 4? These two formulas don't cover everything that could happen. Yep.
On the axis.
It could be on an axis. Now, think about if you had a point on the y-axis. What's the x value of a point that's on the y-axis? 0. And the y value, well, we don't know. Some y value. Could be positive or negative. But the problem is, what would happen if you tried to plug in a coordinate that was on the y-axis into one of these formulas? Why? Because what? Why would, what do you mean, why wouldn't it exist? Nick?
You can't divide by 0.
Right, you can't divide by 0. So any point on the y-axis is going to have an x value of 0. You can't plug in x values of 0 in these formulas. You'd be dividing by 0. So if you end up on an axis, that's a special case. You just have to memorize the 4 answers, 0, 90, 180, or 270. Okay, if you're doing radians, 0, pi over 2, pi, 3 pi over 2. Just to be clear, that's your 0, that's your 90. 180 is when you go left. 270 is down. Now, that covers the 4 special cases if you're on an axis, and it covers the standard cases when you're in a quadrant. So now we should be able to find our angle, no matter what coordinate you're given, and you should be able to find the radius. Now, if you end up with a special case, like a coordinate that has a 0 in it, you don't really need Pythagorean theorem to find the radius. Because, let's say you had the coordinate 0, 5. I mean, how far is 0, 5 from the origin? 5. You don't have to do Pythagorean theorem for that. So I only really use Pythagorean theorem if both parts of the coordinate are not 0. Then it's like I'm finding the hypotenuse of a triangle. Any questions on that? All right, so let's see if we can write this number in trig form. All right, -2 plus 2r. What are the 2 things that you need to figure out to write the number in trig form? What's one of them? Yep, you need r. Okay. And what's the other thing you need? Yep. You need theta. It doesn't matter which one you do first, they're completely independent of each other. Okay, let's start by just making a quick sketch so you know what quadrant you're in, because that's going to affect how you find theta, and it might help you visualize how to find r. So, can someone tell me how are you going to graph the point -2, 2? Where is it going to be? John?
The point's going to be down to left. We're sorry, left to up to.
Left 2, up 2. So there's your point. There's your radius. So the radius here, what's that going to be when you use Pythagorean theorem? Nick?
Square root of 8.
Yep, square root of 8. And what does that reduce to?
2.83.
So I don't want to round it, I just want to simplify it.
Oh, okay.
2 square roots of 2. Now, what kind of triangle is this that we just drew? It's a right triangle, but besides that. Yep.
Isosceles.
It's isosceles, which means these other 2 angles have to be what?
Equal.
They have to be equal and they have to be 45. So technically you don't even need inverse tangent here, because if you know this is a 45, then you know this is a 135. But let's pretend it wasn't a special case where you could just kind of figure the angle out, and let's figure it out like we normally would. So, the formula for your angle is the inverse tangent of y over x. Well, that's x, and that's y. What do you get when you divide y by x? -1. So if you do the inverse tangent of -1, you get -45. But what quadrant is my point in? 2. So go back and look at your formula. If you're in quadrant 2, do the inverse tangent of y over x, which we just did, but then add 180. Okay. So I'm actually going to put that in right here so we don't forget it. So it's 180 plus the inverse tangent of y over x. So that's 180 plus -45. And that's basically 180 minus 45, which is how much?
135.
135. There you go. So there's your angle. There's your radius. Now the final answer has to be written in that form I showed you earlier when we factored out the r. Just change this r to 2 root 2 and change theta to 135. And that's the final answer. All right. r cosine theta plus I sine theta. Now, if you distribute that 2 root 2 out, then you would get back exactly what we started with. So don't do this out unless you want to check your answer. Yeah.
Would theta not be 45?
Well, 45 would be a quadrant 1 degree angle. And we're in quadrant 2.
Okay.
So if you had this, then yes. Now your angle would be 45 degrees and your radius would be exactly the same. But that causes it to be 135. Just remember, this is the angle you're looking for. Like that. Okay. Any questions on that? All right. So, why do we want to write a number this way? Well, kind of hinted at that earlier. Writing a complex number in trig form makes multiplication and division extremely easy. Let's review how we do multiplication or division without this. Right? And then we'll do one with this, and I'll show you how much easier it is. Right? So the trig form of a complex number gives you a very simple way to multiply and divide. And this will be the last thing you look at. All right, so let's remember how we would divide something like this. Yep.
So we would have to times both the side by 5 minus side.
Yep. So,
Conjugate.
yep, exactly. To divide two complex numbers, you have to multiply the top and the bottom by the conjugate. So in the top, we have to FOIL it out. We get 15 minus 3i. And in the bottom, if you remember when you FOIL it, there's a trick here. The imaginary part is going to cancel, and you're going to be left with 26 in the bottom. If you FOIL it all out, you'll see that's what happens. It's 25 minus 5i plus 5i minus I squared. But remember, I squared is what number? It's negative 1. So if you do a minus I squared, you're doing a minus negative 1. So the bottom ends up being 26. Even using that trick to speed it up a little bit, this is still taking a little bit of time to get this done. Then, to put it in standard form, you're supposed to write it as two fractions. 1526 minus 326. And that's how you divide complex numbers in standard form. So we've done that before. What we're really focusing on now is how can we do that a lot easier. So I'm going to show you the formula that you can use to multiply and divide complex numbers. So let's assume you get two complex numbers in polar. I'm calling the first complex number Z1 and the second one Z2. Each complex number has its own radius and has its own angle. So R1, theta 1, R2, and theta 2 would all be numbers in a real problem. It'd be something like that. They'll give you the R and they'll give you the theta, or you'll find it. Okay, but they'll be numbers. If you want to multiply these two complex numbers together, if this was standard form, you'd have to FOIL it all out, get your I squareds, change them to -1, combine like terms. You gotta do all that stuff. In polar, or trig form, all you have to do is two things. Take your two radii that represent each complex number and multiply them together. Take the two angles and add them up. And that's all you have to do to multiply complex numbers that are in trig form. Multiply the two radii together and then add the two angles up. Now, division is pretty similar. Based on that pattern, anybody have a guess what you would do with your two radii if you want to divide two complex numbers? John?
Subtract. Or sorry, with the radii, I assume you divide the radii and then subtract the angles.
Yep, you're going to divide the radii and subtract the angles. Now, radii can't be equal to 0. Radius 2 could never be 0, because then you'd be dividing by 0. But if you look at kind of what's happening here, you might notice something. If you were to FOIL, like let's say you were to FOIL these two things out just the way they are, notice here you get cosine of a sum, and here you get sine of a sum. If you FOIL these out just the way they are, you would end up with the trig identity for the cosine sum formula and the trig identity for the sine sum formula. It's exactly what you would end up with. So the proof of why this works isn't really that hard. And the concept would be pretty similar for this one, right? But we're not, right now, we're not going to go through the proofs of those two formulas. But it does involve the cosine sum identity and the sine sum identity. That's where the formula comes from. All right. Does everybody have those two formulas? Okay. So let me see. I want to go back. Okay. So what I've done here, yeah, we'll do this one. Okay, I've given you two complex numbers. And just to save a little bit of time, I already found the radii and I found the angles. In fact, this is the one we just did in the last example. The radius was 2 root 2. I just did the angle in radians. So instead of saying I think it was 135, I just converted it to radians. So let's multiply these together, okay, the old way, and then let's multiply these together the new way I just showed you, and you'll see how much faster this is compared to doing it this way. Okay. The part that would be a little time consuming here is if you didn't already have the radius and the angle, you'd have to go through and find these. But I'm kind of speeding it up by giving those to you in this problem. And this one we technically already found. So, all right. So let's do, I'm not going to do the multiplication the old way and the new way, and the division the old way and the new way. Let's just do that for the multiplication. So this is the old way. So Z1 is 3 plus 4i, and Z2 is negative 2 plus 2i. All right, so let's FOIL it out. 3 times negative 2 gives me negative 6. 3 times 2i, 6i minus 8i.
Negative 2i.
Negative 2i. 4i times 2i.
Negative 8.
Yeah, so that's going to be 8i squared, but I squared is negative 1, so that's negative 8. And then what's negative 6 minus 8? Negative 14 minus 2i. Okay, so that's how we do it the old way. Now, let me convert that, just because we're going to do the new way in polar. Let me quickly change that to polar, and then we can compare our answer. Because right now, if we do the new way, the answer is going to be in polar. The old way, it's in rectangular. So, actually, you know what? We'll do it in polar this way, and then I'll show you how you can check your answer. And it should come out to negative 14 minus 2i. So let's just do it the way it is. So the new way, all we have to do is multiply these two radii together. So what's 5 times 2 root 2? 10 root 2. Let's just leave it like that. So 10 root 2 cosine, we're going to fill in an angle, I sine, and we're going to fill in an angle. To multiply these two together, what am I supposed to do with my angles?
Add them together.
Add them together. So 2.36 plus 0.93. 2.36 plus 0.93. Okay, 3.29. And that's the answer the new way. That's all we have to do. Multiply the radii and add the angles. Now, to confirm that this is correct, we can distribute this out and see if it comes out to about negative 14 minus 2i. It should, if we did it right. So let's put the calculator in radians. And this is an example of how you convert a number that's in trig form back to standard form. You do this out. And we're just doing it to check and see if it's the same. Let's take 10 times the square root of 2. And let's multiply that by the cosine of 3.29. And we're hoping we get negative 14. Oh, I didn't type in times. 10. It's probably easier if I just type it in all at once. Times cosine of 3.29. Now, we're hoping we get negative 14. Good. Negative 13.99. So we know we did the real part, right? Now let's check the imaginary part. Hopefully we get negative 2. So we've got 10 square roots of 2 times the sine of 3.29 gives me negative 2.09. So basically what we got here, it's off a little bit because of rounding, but it's pretty close.
Could you do it the other way? Could you take the old way and change it to the new way and it's come out 10 square root 2 cosine 2.29 plus that 3.29?
Yep, I could have changed this into polar instead. I could have done it either way, but I wanted to compare the two answers, so I had to do it one way or the other.
So 1, 2, 3, 4. Okay.
Any question on that one? So if we were going to divide them, what do you do with the 5 and the 2 root 2? Divide. And what about the 0.93 and the 2.36? Subtract. Yep. Any questions on that? All right, so you guys have seen the first thing that we're going to do in polar form, or trig form, which is multiply and divide. Tomorrow, the next two things we'll look at are how you raise a number to a power, which is really just multiplying the same thing over and over, and how you do roots. Like how do you take a root of a complex number? Very easy to do, or much easier to do it in trig form. So we'll build on this trig form tomorrow. Okay, so those are the questions for tonight. I think there is some practice there with the old method of doing calculations with complex numbers, and then a little bit with the new stuff as well. Okay, so we'll take a look at that tomorrow. Just a reminder that I will be after school tomorrow if anybody has to make anything up or anybody needs extra help.